Here in this particular section in 4.2, we're just going to look at a couple of small aspects of this particular section in terms of being able to graph polynomial functions. So one thing that is important to be able to understand is really kind of three different characteristics of graphs of polynomials. So if we assume the following, that p of x is a polynomial, and it has degree n, which of course means that the highest exponent in the equation for this is n, then the number of real zeros that p of x has is at most going to be n. So there can only be, at the highest, n real zeros. So if the highest exponent was 12, right, there would only be 12 real zeros. And that's really actually synonymous with saying then that the number of x-intercepts of the graph of p of x is going to be at most n as well. Because anytime there's an x-intercept in a graph, that means it actually corresponds to a real zero of the function, right? So sometimes functions can have complex zeros that are imaginary in nature, and you're not going to be able to see that on the graph, right? So always n is the maximum number of real zeros and the maximum number of x-intercepts. Last thing that I just want to highlight then is the number of turning points of the graph. So remember that turning points in a graph are when it reaches either a relative maximum or it reaches a relative minimum because the function changes from increasing to decreasing or from decreasing to increasing at those particular points. So the number of turning points of the graph of p of x is at most n minus 1. So always one less than the actual degree. So for an example, let's say that we have a polynomial function that we call q of x, and it would equal, let's say, 3x to the 8th minus 5x to the 6th plus 2x, right? So the degree of that polynomial is 8 because it's the highest exponent among all of the different monomial terms. So what that would mean then is that q has at most 8 real zeros of that function, but then also q is going to have at most 8 x-intercepts because that's synonymous with having real zeros. And then for the turning points of the graph, it would have to have 7 at the most or less than that. So the maximum number of turning points is 7. Okay, so each of those 1, 2, 3 things you should be able to identify and know what the maximum bound would be for real zeros and x-intercepts and turning points. And then we're going to skip a whole bunch of stuff here in terms of graphing of polynomial functions and go all the way close to the end of this section here. So we're paging past all of this, and then we're going to get to here the section 2, which is dealing with the intermediate value theorem. So before I state what the intermediate value theorem ultimately says, basically what the kind of intuition behind this is if we have a function that is continuous, so something like this function where it's all connected together, right? And if I pick a couple of different x numbers along the domain of this function, so let's say that I call this x number a and I call this x number b, right? So correspondingly, where a happens, we have this particular y value, which I could call f of a, if we call this blue curve, I guess, f of x. And then where this b value happens, it has a y value at about that height right there, which I could say is f of b, right? So because of the fact that this graph is continuous from that point all the way down to this other point right there, that basically means that all of the y values in between f of a and f of b are going to be hit by plugging in some number in between a and b, right? So we're able to find some number between a and b that we can plug into f that's going to equal every single y value within that range between f of a and f of b. And that's really because the function is continuous and defined between a and b. So this is what we call the intermediate value theorem. And so what the intermediate value theorem is really going to say is we are going to let f be defined on this open interval between a couple of different x numbers of a and b. And also it needs to be a continuous function on a to b. So what we'll be able to say then is that then there is always going to be some x number c that is between a and b. So when I wrote that fancy notation right there, it just really means that c belongs to the interval of a and b. So it's just saying that c is some number between a and b, such that f of c is going to be between f of a and f of b, between those y values. So it's really just a fancy way of saying that there is some x between a and b that we can plug in to get a y value that's somewhere between f of a and f of b. So it's called the intermediate value theorem because intermediate means it's kind of in between, right? And so c and f of c are going to be between a and b and f of a and f of b respectively. So a couple examples here where we're asked to determine whether this IVT, the intermediate value theorem, would apply to each situation. So in the example of the first graph right here, we have the graph of f of x, which equals x cubed minus 7x plus 4. And we want to determine whether it's going to have a real zero on the interval -4 to -2. So a real zero means it's going to have an actual x-intercept, right? And it needs to happen on this interval where -4 is less than x, which is less than -2, okay? So you have to recognize that because this function right here is a polynomial, we know that polynomials are always continuous. So therefore we can kind of proceed to see if the intermediate value theorem is going to apply. So what I'm going to do is I'm going to take this interval of -4, -2, and I'm going to plug in -4, I'm going to plug in -2 into the function and find f of -4 and f of -2. So if we find f of -4, first of all, we're going to get -64 plus 28 plus 4, and that ends up equaling -32 for a y value. And then if we do f of -2, we end up then getting -8 plus 14 plus 4, and that gives us 10 for a y value, right? So what we're interested in is we're trying to see if we have a real zero, an x-intercept, and that means that y would have to equal 0 at that particular point, and we can see that actually 0 is going to be between -32 and 10, right? So kind of visually or graphically seeing what's happening here, then we're going to be able to see then that if you go between -4 and you go between -2, that when x is -4, you have this y value of -32 down here, but then you have this y value right here of 10. So since the graph is all connected, somehow it's going to be able to cross through the x-axis at some number between -4 and -2. So therefore, the intermediate value theorem is definitely going to apply in this situation. And so we will be able to say that, yes, there is some x number that's going to be between -4 to -2. And then I'll just abbreviate, ST just abbreviates such that f of that particular x number is going to be able to equal 0 and thus have a real zero of that function. And then for part B of this here, we want to be able to determine if f of x is going to be equal to 2 between x equals 5/2 and x equals 3. So we'll still use the same function and plug in 5/2 and plug in 3, since we're looking at that interval, and see what we get for y values. So if you plug in 5/2 into f and you evaluate that, let's punch that into a calculator here. We're going to get 5/2 cubed minus 7 times 5/2 plus 4 And that comes out to be 2.125. And then if we evaluate this for 3, we do 3 cubed minus 7 times 3. End up getting 10. So if we want f of x to equal 2, we'll realize that it's not going to be between 2.125 and 10. So really what's happening in this case right here is you have 5 halves right here, and you have 3 right here, and the function starts here and will go up to here at a height of 10, and then here at a height of 2.125. We want to try to figure out where f of x is going to equal 2. And so it's not necessarily guaranteed that the function is going to actually equal 2 in between those numbers. Now, it might be the case because maybe the function actually dips down and comes back up and hits 10 again. So maybe, but it's not going to be guaranteed because that y value is 2 is not between the f of 5 halves and f of 3. So therefore, we can't be certain. So the intermediate value theorem is not going to apply in that case. And we can't make any definitive conclusions about f of x equaling 2 on that interval.